Okay, next up is Ciara, and she is going to talk to us on Dobble, more than a playing game.
Okay, so hi, Dobble is also known as Spot It, and this lightning talk is a brutally cut down version of a full talk, which is called Finite Geometry in Card Names by my good friend Julian Godawata. His email there, juliancgwt@gmail.com. If you'd like to see a full version, then you can email them. Now, my household, like many others, got a copy of Dobble in Christmas 2018. It's a deck of cards, and each card has 8 symbols. And actually, each card matches every other card on exactly one symbol. So when you're playing these games, you know you always have a match. It's just your job to spot it. So if anyone wants to quickly try and spot it here, I can tell you that they match on the treble clef. And it's super fun to play. And it was all fun and games until I started to think about how this actually worked. And much brain hurt and drawing pictures and Googling ensued, because Dobble comes with 55 cards with 8 symbols on each card, and every single card matches every other card on exactly one symbol. So that's 1,485 possible pairs, and they've managed to construct each set of 8 to satisfy all these pairings. Now, with some persuasion, I looped in my good friend Julian, who studied mathematics, to help me make some sense of what I found, and they produced this wonderful presentation, which I've cut down for you here. So how does one create a game like this? Well, what maths allows us to create such games, and how far can we take it? Is it even always possible? The idea is to represent the symbols as colored dots, and then we're going to use each line to represent a card. So we're using this line here to represent this card with 5 symbols instead of 8, which are in real Dobble. 2 cross lines represent a pair. The color they cross at is the symbol on which they match. And now we need to actually define the rules. So in Dobble, any 2 cards share exactly one symbol. This means any 2 lines meet at exactly 1 point. Rule 2 is that any pair of symbols will appear on one and only one card, which means that any pair of points is connected by exactly 1 line. And finally, rule 3 requires that we have at least 3 points per line and at least 2 lines, and that's just so that we end up with actually interesting solutions. And these constructions that we care about are actually called finite projective planes, which have their own Wikipedia page. So how do we start? Well, if we want 8 symbols per card, like in Dobble, it turns out to be very helpful to consider the value just below, so 7. And we're going to label this n. And now, using this n, we will soon see that we need to have n squared plus n plus 1 cards and symbols. This means that if n is 7, we get 57. And if n is 3, so 4 symbols per card, then you get 13 symbols or 13 cards. But how do we construct them? Well, we've got the number of symbols, we've got the number of cards, and we've got the number of symbols per card. But if we try and brute force this, even for just n equals 3, it's actually kind of a pain. And it turns out we can get what we want by moving into 3-dimensional space modulo n, which produces a cube like this one. So in this example, we've taken n to be 3. So all of space has been reduced to a 3 by 3 by 3 cube. So we now need to consider how many unique directions out of the origin there are, remembering that we wrap around and we don't want any parallel lines. With a little bit of thinking construction, we can see that we get n plus 1 directions from the origin to the points on the front plane and n squared directions from the middle plane, which wrap around to cover all the other remaining points. So n squared plus n plus 1, like I mentioned earlier. But how do we get to Dobble? Well, this is where the magic happens. We're going to take all of these lines and condense them purely into points by projecting them into 2D space. And then just as 2 points in 2D space create a line, their corresponding directions in the cube can be combined to create a plane. This construction is clever because in the cube, any 2 planes through the origin intersect at exactly 1 line, which equivalently means that any 2 lines meet at exactly 1 point in the 2D configuration, satisfying rule 1. And then because any 2 points will be joined at exactly 1 line, we satisfy rule 2. And now we can just insert the symbols and find we have our cards. And that's cool, even more so because we can actually use it for any prime n. And that's by virtue of the fact that doing prime modulo arithmetic on any number on a set of values from 0 to prime minus 1 gives you back your set from 0 to prime minus 1. But it turns out this construction actually works for all prime powers. But for other numbers, it's actually an open problem, hence my frustration gif there. And as of 1989, we know that for n equals 10, this definitely does not work, which is proved by 2 years churning through sets on a computer. But for n equals 12, we actually don't know. It's an open problem as to whether or not you could have 13 cards on your Dobble card and create a set that would satisfy it. So my pondering of this simple game of Dobble took a lot longer than expected and required me looping in a friend to help me understand it. But the conclusion is just that Dobble is for life and not just for Christmas. If you want the full version, which I would recommend, because there's a lot of more info that I rushed through here trying to explain, then yeah, definitely research it because it's quite cool for a kid's game. And that's me done.
That is awesome. Thank you so much. I think you've just turned a game into maths. I'm not sure what I think about that. What should you do if your compiler keeps saying, "What's up, Doc? Look for bugs in your code"?